Okay. What else? Anything else I should say, Sabina? Okay. So we've got, how many people? We've got 64 people. Should we give you another minute or should we start now? People no longer have the excuse of, I just had to run here because that doesn't qualify anymore. Sorry.
I think this is a background contribution.
I think, well,
I think the host can mute people.
Okay. Maybe you can mute phone call. I think that's where it's coming from. And let me also remind people, unless you're asking questions, you should probably be muted in general.
Who is the host? Because the host can just go and mute a few people that are unmuted.
You're the mute host? Okay. Because there's someone with a little child who's we enjoy the child's conversation, but it might not be helpful here. So should we begin now?
Yeah, let's do it.
So thank you for coming to the AI seminar. I'm Russ Greiner. I'm one of the Amii Fellows. If you're interested in being a member and finding more about the AI seminar, send email to Sabina. I guess you're coordinating it in general. Today, we're very fortunate to have Mark Schmidt. He's one of our new CIFAR Canadian AI Chair with our center. Several presentations in the next several weeks. Other fellows coming in. A little bit of context. I've known Mark for many years. He did his master's degree with me many years ago. I then did something which was good for him. I told him he should, as he did his bachelor's at U of A and he did his master's, he should now go elsewhere for his PhD. That was a bad move on my part, but it was good for him. He went to UBC, did his PhD there, did various other fellowships and things. And now he's back at UBC as an associate professor at UBC, looking at machine learning and numerical optimization. He also is the Canadian Research Chair and an Alfred P. Sloan Fellow, as well as a CIFAR Chair. He also just got an amazing award, Lagrange Prize in Continuous Optimization, which is very impressive. And today he's going to talk about, where's your actual title? I remember I had a question mark in it. He's going to talk today about faster learning for deep learning with a question mark after it. So I'm going to find why the question mark's there. So Mark, one more thing. If you want to speak with him, there's a few slots in the afternoon available. I'm going to talk to Sabina about that. Okay, thank you. Mark, all yours.
Okay, can people hear me? Okay, great. So first off, thanks for the introduction, Russ, and thanks for having me speak today. I'm definitely super happy to be associated with the U of A in some way again. I definitely have fond memories of there, and I was technically born on campus too. And I don't know if this is true or not, but I think I may have come to the very first one of these pizza talks, if the first one happened in 2003 or so. Okay, I'm going to try and share my screen now. Hopefully that'll work. Someone will just have to yell out because I won't be able to see you once I start sharing. Okay, can you see?
Yes, we can see it.
Okay, perfect. Now I'm going to get rid of myself here.
Oh, I should ask Sabina, if people have questions, they should wait to the very end and ask them, or they'll put it on chat. I forgot to ask that earlier.
Oh, I'm actually happy to have questions, but if we get a bit too derailed, I'll maybe say that we can take stuff offline or that I'll just finish and we can come back to things and so on. So feel free to yell out, but I may cut stuff off at some point in time. Okay, so today I'm going to talk about faster algorithms for deep learning, question mark. And I've only listed myself, but I'll mention many co-authors throughout the talk. I'll also warn you, sometimes my internet cuts out for 5 minutes for no reason, so I'll try and come back online as soon as possible if that happens. Okay, so start of the story. 2006, shortly after I left U of A, I went to a workshop by something called CIFAR, which is now called CIFAR, about this thing called deep learning. And this character, Jeff Hinton, gave a talk where he showed this demo. And I was thinking like, oh, that's interesting, that people seem very excited about this. But something weird is they were using this algorithm called SGD. And it's from 1952, and it's notoriously slow. So this was my, there was no Facebook back then, but this was what my first profile picture on Facebook looked like. And I just was still doing swimming and so on. And I was thinking that I'll have a huge impact if I can develop a faster algorithm for these deep learning models. So to give some context on SGD, usually when we fit a machine learning model, we fit parameters by minimizing some sort of expectation. So you have parameters x, you have some function fi of x. So x is your parameters, I would be training example I, and f is some function that measures how well you fit training example I. So that might be the squared error, or your logistic loss, or your cross entropy, or whatever. And then we take the expectation over this value of I. We take the expectation over all training examples you could possibly see. So one of the most common algorithms in machine learning for minimizing problems like that is stochastic gradient descent, or SGD. And so just to give you my notation here, you start with some guess x0, and then you generate a sequence of guesses xk. To go from xk to xk plus 1, you subtract a small step size alpha k times some number g of xk. So just to reinforce the notation, we have an iterate xk, which is our guess of the parameters on iteration k. We have a step size alpha k, which is how far you move on that iteration. And then you have this direction g of xk. And usually the assumption is it's an unbiased estimate of the gradient of the expectation. And the easiest way to get that is you take the gradient of a randomly chosen example, or you take the average gradient of a mini batch of examples. There are various ways you can relax that, but that's the standard setup. Okay, so these are pictures I've stolen from Francis Bach illustrating gradient descent versus stochastic gradient descent. So in gradient descent, you start at some point, and we're imagining these are the level curves of a function. So here's the minimum, and then the function gets bigger as you go up. So it's like a hiking map where you're trying to hike down the valley. And gradient descent makes these right angles at each step with the level sets, or at least they should be right angles. This is not quite drawn properly. And you make steady progress towards the minimum. And so stochastic gradient descent might look more like this, where you're not making these nice right angles anymore. You're going off in weird directions. You might go in directions that increase the objective function. You start out with big step sizes, but your step sizes slowly get smaller, and you still approach the minimum. Now, I think this algorithm is very generous to stochastic gradient descent. It actually doesn't work as well as illustrated here. It's usually quite slow and quite erratic. Okay, so the big advantage of SGD is that the iteration cost is O of 1 in terms of the number of examples. So if you have 1 billion training examples, it's 1 billion times faster to do an iteration of stochastic gradient descent than gradient descent. Because instead of computing the gradient of every training example, you just compute the gradient of one training example. And the other advantage is it often works well for training deep neural networks, or at least it's quite difficult to beat. The disadvantage is really due to the variance in the gradient approximation, the fact that you're using a random example to approximate the gradient. So because of that, you may need a huge number of iterations to get near the optimum. It may be sensitive to the choice of the step size, and you don't really know when to stop. And so these are really the three issues we would like to address. So let me just pause there and ask if anybody has questions about the notation or about the setup or anything related to these issues before I dive into sort of our approaches to try and speed up this algorithm for deep learning. I'm very patient.
Let me ask the meta question. Are people able to ask questions? People know you can unmute and pose questions if you wish.
Yeah, I would definitely recommend unmuting if you're going to ask questions. Muted questions are unlikely to get answered, but yes, you can definitely unmute yourself and ask questions if you like. Okay, I'm gonna move on. Okay, So the classic work on trying to analyze how SGD works focuses on these things called convex functions. They maybe look like this in 2D. The key property that we often use of convex functions is that all the local optima and all the stationary points are global optima of the function. So if you can just find a stationary point, you've solved the minimization problem. So that led to me to some reasoning that maybe I should focus on convex objective functions. And this reasoning might have been flawed. So one of the reasons to focus on convex functions, well, it's easier to prove things. We really only knew how to analyze SGD for convex functions at that time. Another reasoning might be that if it doesn't work for convex functions, it won't work for non-convex functions. So we know that deep learning objectives are convex near the solutions. Really, any objective function near a minimizer is going to be look like a convex function. So that reasoning seems sound. But ultimately, another reason is we didn't know how to analyze SGD for non-convex functions at the time I was thinking about this sort of thing. So you might ask this question: how many iterations of SGD do you need to minimize a convex function? So this was basically known in the 1950s, even though those papers are quite hard to read and they were using quite different notation and assumptions. But basically, you assume the function satisfies something called strong smoothness. And for those of you who've taken real analysis, this is just saying that your gradient is Lipschitz continuous. And then something called strong convexity. So it's a little bit stronger than convexity, but for most convex objective functions in machine learning, they're also strongly convex. And then, so those are standard assumptions you use to analyze gradient descent. To analyze SGD, you also assume that the variance of the gradients is bounded, that the g of xk's can't be too crazy, that there's some limit to how much they can vary compared to the true gradient. And then what was shown is that if you want to get with epsilon close to the solution, SGD is going to need O of 1 over epsilon iterations. So this may look a little bit weird if you haven't seen something like this before, but you're imagining epsilon being very small, and so 1 over epsilon becomes very big, and so you can think of 1 over epsilon as sort of like number of digits of accuracy or the exponential of that or something like that. So if we compare that to deterministic gradient descent, you would only need the logarithm of 1 over epsilon. And so from a computer science perspective, I would really say that this one is like a polynomial number of iterations, and this one is really like an exponential number of iterations. So if we're coming from a computer science perspective, we shouldn't really be happy with the number of steps of SGD that we have to do. And unfortunately, there's some bad news, which is that if your method is just based on getting unbiased gradient and unbiased function value at each iteration, you actually cannot go faster than 1 over epsilon in terms of the dependency of epsilon. This is true even for one-dimensional problems under the above fairly strong assumptions. So it's kind of bad news. You might think that you can do better by getting approximations of second derivatives or using momentum or something called Nesterov acceleration. But actually the lower bounds hold even in those settings. So, and that's because the lower bounds come from the variance on the gradients, they don't come from the condition numbers. So things like Newton's method and Nesterov acceleration, they improve your dependence on the condition number, but they don't improve the variance, and so they can't let you get around this lower bound. So in order to get around this lower bound, we can't use those assumptions. We need to add some extra assumption because otherwise it's actually impossible to develop a faster algorithm. And so over the past many, many years, I've basically explored two approaches to get these faster rates for an SGD style method. The first one is you assume you only have a finite training set. So you assume that there's some number n, and you only have those n examples, and you're just going to focus on optimizing the loss over those examples. So this is pretty standard. Usually you don't have infinite data, so maybe you can design an algorithm that exploits that property. The second approach is we're going to cheat. We're going to assume that SGD works and try and find the assumptions that show that it works really well. And maybe if those assumptions are not too ridiculous, you could explain why SGD works so well, and maybe this will also suggest new methods that might be even faster. Okay, and so just to actually let me go do one more slide, and then I'll pause for questions and comments. So this is a plot I've shown many times. I think I've even shown it in this seminar a few years ago. So what I'm going to plot here is time, or rather number of gradients you calculate. And here is the log of how far you are away from the optimal solution. So if we use deterministic gradient descent, where you go through the full data set on each step, you do very little for a lot of time. So you compute the gradient on the first example, second example, third example, up to nth example. Then you take your gradient step. Then you go through your data set again and take your gradient step, and so on. Now that's in contrast, but you make steady progress. So every time you make a step, you make a lot of progress. So in contrast, the stochastic method, you take a gradient, take a step, gradient, take a step, gradient, take a step, and so on. And in the first pass through the data, you make a lot of progress. But the more steps like this you take, because of the variance, you start to go slower and slower and slower. So yeah, that's the time to go through all in examples. So you can think of gradient descent as a method that makes consistent progress with slow iterations, and stochastic gradient descent has fast iterations but makes less progress over time. And neither algorithm really dominates. So if you reach your optimal test error at this level of accuracy, then you should use stochastic gradient, because it gets you there very fast. Whereas deterministic takes a lot longer. Whereas if you need this level of accuracy, then you'd rather use gradient descent. Similarly, if you have so much data you can only spend this much time learning, you should definitely use stochastic gradient descent. But if you have this much time, you should use gradient descent. Okay, I'm gonna pause here and let people ask questions, and let my wife make some noise in the kitchen.
Hi, Mark. Can I just ask how this might relate to the overfitting? Where does overfitting play into this kind of chart that you've got here?
Right, so overfitting is a bit tricky. In principle, overfitting, like if we plotted overfitting on another axis, we would expect overfitting to basically go up over time. And I'll get into the issue of overfitting a bit more later, although I won't go as far as like double descent curves in the modern view of overfitting and so on. I do have separate slides on that if people want.
I have a question. If you have a very, very simple neural network which just has a linear function, and the goal is to approximate that function on a compact set, so it's bounded and everything, what would be the rate of learning in the current kind of neural network for just a linear function in the most simple conditions?
So rate of learning in terms of time or in terms of number of training examples?
Well, I guess the number of training examples, yeah.
So in terms of number of training examples, under the standard assumptions, if you had a sort of a small network, it would actually be 1 over epsilon in terms of number of training examples, whether you're using SGD or whether you're exactly minimizing. So that comes from various sources. In statistics, it's called the Kramer-Rao bound, or ERM if you look at Vapnik's work and so on. So in some sense, that's how fast you can learn in terms of data. But some of the things I'll talk about later in the talk sort of violate this and show you can go faster in terms of learning with stronger assumptions.
Thanks.
I have a question on the upper stochastic graph. So it looks like it does not converge at all. It would seem to me with a step size that gets smaller over time, and the convex function, it would converge, or does it converge or plateau the way you draw it? It was unclear in your illustration.
Yeah, good question. So it does converge. This is what an O of 1 over epsilon convergence rate looks like. So it's converging, but it takes an exponential number of iterations to reach a given accuracy. So it will eventually converge. It's just, it's very, very slow. It's sort of like convergence to the harmonic series type of thing. Like the harmonic series diverges, but it diverges like incredibly slowly. Now, the plot I've shown here is with a decreasing step size. If you use a constant step size, the plot looks a little bit different. It may go down a little bit faster at the start, but then it'll bounce around and it won't converge. So I've sort of drawn the decreasing step size version here.
So I have one quick question, and this might be a very, very stupid question, but is it possible to do SGD then for a while and then swap randomly to deterministic to get the best of both worlds?
Okay, so that's the initiator of the next slide. So probably everyone on the call can think of some sort of hybrid method. So there's a whole bunch of hybrids you can think of. So maybe you initialize with SGD, and then you switch to the deterministic method. Or maybe I think Martin, you may want to mute now.
Okay.
Or you can increase the batch sizes over time, and that'll work. So you can get something that follows the stochastic at the start, and then looks more like deterministic as you go along. There's many ways to do that. The things I'm going to mention first are actually better than doing that. And my wife is trying to
I just dumped my spaghetti.
burn down the kitchen.
No, I just dumped the spaghetti.
Okay. So these are called variance reduction methods, and they sort of not only get the best of both worlds, but they can actually be even faster than hybrids. So not only are they fast like stochastic at the start, but if you look at the slope is actually steeper than the deterministic gradient method. So these are all about using finite training sets. And these are methods that have the cost of stochastic gradient, but they have the progress of full gradient. So in each iteration, they only look at one training example, but they make as much progress as if they were looking at all training examples up to a constant. So in terms of math, you need log of 1 over epsilon iterations to reach accuracy epsilon. So it looks like that nice curve where it's going down and it's obvious that it's converging, but you only have an O of 1 iteration cost. So if you have 1 billion examples, it's 1 billion times faster. The idea behind these methods is you design an estimator of the gradient where the variance is going to 0 and it actually converges to the true gradient as you run the algorithm. The first general method that achieved this property was our method. It's called stochastic average gradient, or SAG. The key idea is you keep a memory of the previous gradient value for each example and use those to design an estimator. That won't work for neural networks because that memory will kill you. But a year after we proposed that, there was another method that came out that didn't have the memory. It was proposed by several different people at the same time. They gave it different names, but SVRG is the common name for it now, and it looks like this. So the first few terms are actually just the regular SGD iteration. So if you have an SGD code, it isn't much of a modification. And then what you have here is called the control variant. And so what's happening is you have this old iteration x tilde k, which is like a snapshot you can think of. And at that location, you're going to subtract the gradient at that location, but then you add the gradient over all examples at that location. So this algorithm occasionally requires you to compute the full gradient, and then on each step you compute these two gradients and look at their difference, combine that with your old full gradient, and that's the direction you go in. And it has this same property that it only needs I guess it needs two gradients on each iteration, and it only needs log of 1 over epsilon iterations to get within some epsilon accuracy. You may be wondering, how often do you update that reference point? In most analyses and implementations, it's something like O of n iterations. So basically, you spend half your time computing full gradients and half your time doing stochastic gradients, but that actually works better when you use this iteration than doing each of those things on their own. So this has led to faster methods in a whole bunch of different settings. So we now have methods that are provably faster for many least squares problems and logistic regression, PCA, cryo, EM, imaging, conditional random fields, and so on. So below I'm just showing some experiments. So here we've got like the usual stochastic gradient methods that start out very fast, but then we see they sort of flatten out. And then we've got deterministic methods like LBFGS that start out slow, but then they eventually catch up and they may even pass. Here we've got a hybrid method that tries to combine the two, and it just basically makes the LBFGS go a little bit lower. And then SAG, for this problem, it worked quite well. For this problem, it wasn't quite as well, but then we had some other tricks with line searches and sampling non-uniformly that actually make it work extremely well. So this has led to faster algorithms in a whole bunch of settings. And that was 2012. That was 8 years ago. So this has now gone in a ton of different directions. So there's now versions that get rid of the memory in some cases. There's variants that work for non-smooth problems. There's variants that work for some non-convex problems like PCA. There's versions with acceleration. There's versions that show that these methods can actually give you better test error constants than SGD. There's parallel and distributed versions. And then we won an award for this work. So in 2018, we won what's called the Lagrange Prize in Continuous Optimization. And they gave us a little medal. And so these are my co-authors, Francis Bach and Nicolas Roux. It's not so easy to get medals for research, so that's kind of neat. Yeah, so that's sort of where that work went. And I'm actually not going to talk much more about this for something I'll mention momentarily, but maybe I'll pause and just see if there's any questions or discussion points people want to bring up at this point.
often when we choose between a gradient or a second order method, most people will just think, okay, a second order method could be too difficult to represent because of the many variables. But it seems to me that also properties of both the function and the variance would affect whether a second order method would be better or not. The way you showed the Royden-Fletcher-Goldfarb method kind of being in the middle of the pack, it would seem that that could be, either worse or better compared to the single gradient methods.
Yeah, absolutely agree. So this method is not faster for every problem, but there's like a certain range of condition numbers and variances where this method is quite a bit faster than previous methods. If the condition number gets too ridiculous, then you absolutely just need second order information. And then that has to be traded off against the number of training examples too. So just to give some more context, if you have a second order method, you actually, up to some hand waving, need log of 1 over epsilon. So it's even faster. But the issue is that's the dependence on the condition number, but on the variance, you still have this 1 over epsilon. So if your variance of gradients is very, very small, then you're better off using a second order method, where if the variance is huge, then the second order method can't really do very much because it's really affected by this part of the lower bound.
Just to clarify, other than this last slide, is everything you're talking about in the context of strongly smooth and strongly convex functions?
The previous slides, yes, but this slide is sort of arguing that they've been extended to non-convex, non-smooth. So it's sort of everywhere these days.
Okay, great, thanks.
So if someone hands you a problem, obviously it's something you want to try. Are there fast ways to say, actually, it was a bad idea to try it? I should just stop and go to a more traditional method?
So if you can quickly evaluate the gradient, like it only takes a few seconds to evaluate the gradient, just use the quasi-Newton methods. They're very reliable. There's no tweaking. The convergence theory is very understood. It's really when you have like big problems, like problems that are so big, you really have to worry about like, how do I store the data and things like that. And not everything will fit in RAM. That's where it starts to make a big difference. So you need to have a large number of training examples, and then the condition number can't be like too crazy. The condition number has to be like less than like 1e to the 10 or something like that. That's a rough guide.
Okay, yeah, good heuristics.
Okay, so nobody asked it, but someone might be thinking, does this work for neural networks? And if I work on neural networks, why have I never heard of this stuff? So this stuff, despite the logic being correct that it helps on some non-convex problems, for deep learning, it doesn't seem to help at all. It seems to make basically no difference and possibly even makes you go slower. So something weird is going on. Okay, so let's go back to my assumptions. I wanted to go faster than this exponential number of iterations. And so we thought about two different things back 10 years ago or so. So the first thing is we said, well, let's say we have a finite training set, and that led to things like SAG and SVRG. That led to faster algorithms for many problems in machine learning, but not really for deep learning. So let's talk about the second approach. Let's say that maybe SGD already works well, and our assumptions were too weak. Maybe we can find stronger assumptions under which SGD actually works, and maybe that explains why SGD works and suggests different methods we should be thinking about. So we asked this question: what conditions would we need for plain SGD to converge fast? And the thing that other people came up with, or other people had previously explored, was something that looks like this. So let's see what's happening. We're taking the expectation over training examples of our unbiased gradient estimate, g of xk, take the norm of that square, and we're saying that's less than or equal to some number rho times the norm of the true gradient squared. So this condition was found, or was first used by Paul Tsang and Mikhail Solodov, some very serious optimization people. They were looking at this in the 90s to analyze SGD on neural networks, and to argue that if you have, they basically showed that if you have this sort of condition, then SGD will converge with a constant step size. You don't need a decreasing step size. So yeah, they showed that this converges under constant step size. Why is that possible? Well, let's think about what happens near a solution. So if I have X star here, if I have the solution there, then this gradient is equal to 0. And so what that means is, with this being a positive quantity, it means this expectation is equal to 0 at the solution, which means there's no variance at the solution. All the gradients are sort of 0, effectively. And so then you don't need a decreasing step size anymore. The decreasing step size is to control the variance. Here the variance automatically is controlled. So there's a small enough step size that SGD will just work under this assumption. On the other hand, when you think about that, you think that, well, it's a very strong assumption. It means that the gradient has to be 0 for every training example. So if the overall gradient is 0, every single training example has to have a gradient of 0. Another way to think about that is the model is actually fitting the data exactly. It can interpolate the data. So if you have a regression problem with data points like this, your line is going I can't even draw it, but your line is exactly going through every single data point in order for the gradient of all of those to be 0. So just looking at that as a picture, if we look at near the solution in the usual setting where we just have a bounded variance, at the solution, if you look at all the gradients of your different examples, they basically have to be pointed in different directions so they cancel out and equal to 0. Under this assumption, all the gradients are 0 at the solution. So there's no canceling out you need to do. You don't need to fiddle with the step sizes to make it converge. So yeah, you don't need the step size to go to 0 to counter the variance. So in this setting, you don't really need variance reduction. Variance reduction is inherent in the problem structure. And so what you can show is that if you just have that assumption in addition to the usual assumptions, and you can get rid of bounded variance, then regular stochastic gradient descent only needs log of 1 over epsilon iterations. So in this case, in the language of optimization, stochastic gradient has a linear convergence rate instead of a sublinear convergence rate. So in this setting, there's no need to use variance reduction, things like SAG and SVRG. And in fact, it would actually slow you down. So the convergence rate, the constants are actually worse if you use variance reduction than just plain SGD. So in 2013, we wrote that up in a 5-page paper. We put it on archive. We never submitted it anywhere. And then we moved on with our life. So this is the entire 5-page paper we put up because we couldn't think of any problems where this is satisfied. We said this assumption is ridiculous. You have to fit all your data points. If you were doing that, you would overfit like crazy. So why would you ever do something like this? Okay, so I'm going to actually move back one slide and just ask if there's any discussion points. Or 2 slides. Let me go back to here, just because that has the actual thing, and ask if anyone wants to bring anything up at this point.
Yeah, I mean, fitting your data points, for example, for classification, if you have 2 classes at 2 different numbers, you have perfect values. So total perfect fit would be fine in that case, I think, unless the classes, of course, are mixed.
Yeah, so if you're linearly separable, this happens. And in theory, you could use a kernel that can fit any data set, or you can make your neural network big enough to do that. And we just didn't think of that stuff in 2013. We couldn't, because if you got a regularizer, this doesn't work anymore. You lose this condition. So you have to have a model that's powerful enough to fit everything, but no regularizer.
Thanks.
I might be jumping the gun here a little bit because I can kind of see where you're going with this. But maybe in the setting in the future where our data sets get large enough and our models get smaller compared to what we're modeling, do you think this condition will be violated and say the accelerations you did are going to be more useful?
Yeah, so if you're fitting like a small neural network, the stuff from the first part of the talk is probably more relevant than the stuff I'm about to cover. And so conceivably, if we get to a point where we get so many data that CNN parameters don't look very big, then variance reduction will probably have a place again.
I'm sorry, you said the previous ones, the variance reduction methods didn't work really well for deep learning, and the assumption was finite data set. Now, is this assumption violated or kind of violated because the data sets are big, or do they not work well despite these assumptions, like despite the fact that these assumptions hold?
Right. So the issue is not in deep learning, it's not that the data sets are too big. The variance reduction still works great with very large data sets. And there's even methods that clean up the constants and so on to get rid of dependence on n. The issue is actually, and actually that probably leads into the next part of my talk. The issue is that there's more assumptions going on in the deep learning problems that make the problem easier. And so variance reduction is in some sense too complicated of a tool. It's more than you need to deal with the variance.
I had another question. So all the derivatives being zero, how does that necessitate that the residual is zero? I could see that could happen for classes of basis functions, such as the polynomials, where the Relo type neural networks is a special case. But does that true for any set of basis functions or any optimization problem?
I'm not. Maybe you can rephrase the second part of the question, but the first part, if you have like a least squares problem or something like that, if the residuals are zero, then the gradients are zero.
I agree to that part, but not the reverse part, that the gradient's zero. Why does that show that the residual is zero? Isn't that the direction you're going?
Yeah, that's fair enough. So the condition we really need is the gradients being zero. And for most machine learning models, if you fit the data points exactly, it implies that. But there could be problems where the gradients are zero, where you're not overfitting the data, or where you're not interpolating the data. I agree. Okay, so let me move on. So I'm just going to slowly go back to where I was. So this is where I stopped. That was our 5-page paper. People emailed us and saying, why aren't you trying to publish this? And we said, we don't believe these assumptions are true, which maybe we should have thought about more carefully at the time, but in any case, life goes on. So the next year, this optimizer called Atom came out, and it became extremely popular for training deep models. But if you just look at the algorithm and you have a bit of background in SGD, you realize that this thing doesn't converge in general. So for some convex functions, this algorithm actually has very poor performance, which violates my assumption on like slide 3 or 4, where I said if it doesn't work for convex functions, it won't work for non-convex functions. And so this led me to saying, like, what is going on here? And around this time or a little bit later, a bunch of groups observed that the deep neural networks that people observe in practice can drive the training error to zero. They can get zero classification error. So here are some plots where you just take a 1-layer neural network and you increase the number of hidden units. And as you see, the error goes down, the training error goes down to zero, which means you're finding the global optimum. So it isn't a matter of different global optimum that are the issue. But the weird thing is also, so that means that this assumption might be true, but even the weirder thing is that the test error goes down if you set up your experiment in certain ways. And so that got me rethinking about this old idea that maybe saying you can fit the data exactly is not such a ridiculous thing. Yeah, so that's what I just said. And then this paper came out in ICML in 2018, and they showed that if you have interpolation, then SGD has a linear convergence rate. And linear means this O of log of 1 over epsilon that I mentioned on the previous slides. So it's a very nice paper. They give some theoretical justification for some heuristics that people use in practice for setting the step size for deep learning. They also discussed the connections between interpolation and the gradients being zero and over-parameterization. So I'm kind of just going to say over-parameterization from now on. And what I mean by that is that you have so many parameters, you can drive the loss to zero. And I'm assuming that zero is sort of the minimum possible value. So that's true for many modern deep neural networks. So we know that a lot of the vision CNNs that are used in practice can drive the error to zero. This is also true for a bunch of the RNNs. Although I haven't expressly gone through the literature and checked it everywhere. It's also true for like linear models if you have a sufficiently expressive basis. So if you use a high enough degree polynomial or RBFs or whatever, you can also fit the training data exactly. And you can also just make this true. So if you make your model more complicated, you can just make that strong growth condition true. So it's a very weird phenomenon because normally we think of making your problem more high dimensional makes the optimization problem harder. But after a certain point, you can fit the data example. And at that point in time, you have this weird thing where adding more features actually makes SGD go faster. And then around this time too, a bunch of groups are exploring what they call the implicit regularization of SGD, arguing that if you fit SGD, the global minimum you find may not ridiculously overfit. And so all this taken together kind of means that, the stuff that we dismissed so quickly in 2013 might actually be a lot more relevant than we thought. We just weren't thinking about it properly at that time. So there's a big connection between our 2013 paper and that 2018 ICML paper in the fact that if you make the assumptions they made in their paper, they imply the assumptions we made in 2013. So their result is actually like implied already by it implies the, I mean, our result already covers the result in that ICML paper. So that made me think that, well, maybe this assumption is not ridiculous in applications, all these things put together. So maybe if we take this perspective that maybe deep learning satisfies this strong growth condition, maybe that could explain the behavior for deep learning. So for example, it would explain why variance reduction doesn't seem to help. So if this assumption is true, you shouldn't use variance reduction. It would also explain things like ADAM, or things like using a constant step size for 20 passes and then a different constant step size for 20 passes and so on. Those would be bright things to do if this assumption was satisfied. Do I think this assumption is satisfied for every neural network model? Probably not. It might just be close to satisfied, but it's sort of like the best assumption that I have in terms of explaining the practical behavior of these stochastic algorithms when you're training neural networks. So we just decided to go with it. We said that maybe this is a good model of how fitting neural networks works. So maybe let's just assume that assumption is true and then see what that suggests. And that led us to some new analysis of existing algorithms and some new algorithms too. And so I'm just gonna briefly describe those to wrap up here. So we have a fast analysis, a faster algorithm, a painless algorithm, and a furious algorithm, which I'll mention shortly. Let me show you the first result before we jump into other discussion. So our first result was in AI stats last year. So all the previous results, assuming this growth condition, assumed your functions were convex. So obviously they don't apply to neural networks. So we showed a non-convex result for plain old stochastic gradient descent. So there's a lot to unpack here. It's kind of weird. So what we're showing is that the minimum gradient you see, the minimum expected gradient you see, is less than wherever you start, basically times some constants divided by k. And if you turn this around, it basically implies you get a small gradient. You get something close to a stationary point after O of 1 over epsilon iterations. And so that's kind of nice. A lot of old results about SGD are for convex. This is a non-convex result. The reason you have to use this weird measure of progress is because it's non-convex. So you don't expect to find the global optimum in general, but so you just have to look at how big the gradient is. Now the neat thing about this result is this is actually faster than all previous non-convex stochastic results. So there's some very fancy papers that have come out in the last few years showing you can make this modification to SGD and go from 1 over epsilon to the 4, or 1 over epsilon squared to 1 over epsilon to the some fractional power or whatever. This result shows that if that assumption is satisfied, just plain old SGD with a constant step size is basically optimal. It in some sense can't actually really be improved. This also, in my book, gives justifications for using constant step sizes in practice. And it also, with a little bit of hand waving, justifies using things like ADAM when you're in this over-parameterized setting. The authors of that ICML paper later gave a result, another non-convex result, where they looked at something called the PL inequality, which allows some degree of non-convexity, but it doesn't quite cover neural networks, because if you have the PL inequality, it still implies all minima are global minima. It implies something called invexity. And so it's not, it's a faster rate, but this rate is sort of applies to any real non-convex function. Okay, so let me pause there on that sort of complicated result and ask if there's any questions or comments or anything people want to make at this point.
So the decrease in loss with over-parameterization, was that the double descent feature?
I haven't talked about double descent. I'm not going to cover double descent in this talk. So the double descent arguments are just an argument that using over-parameterized models may not be a ridiculous thing to do when using certain optimization methods. So I'm not really going to talk about overfitting. I'm going to talk about optimization in this. But double descent could be used to justify using these over-parameterized models.
Makes sense. And so SGC, if SGC is satisfied, what methods work well? Sorry, I forgot.
So if SGC is satisfied, it doesn't really affect deterministic methods at all. So like whether a quasi-Newton method works or not isn't really affected by this. But if SGC is satisfied, then stochastic gradient methods that don't have any way of dealing with the variance can still work. So things like SGD with a constant step size, SGD with momentum where the momentum doesn't go to 0, things like atom, or if you want to use A to grad but not decrease the step size, all that stuff can work under SGC.
Good, thanks.
I'd like to ask a kind of a different question, if I may. If you look at a child learning how to recognize digits, 0 to 9, say, and the kid's got it perfect. And then he goes on to learn the alphabet. Now, it seems to me that if you have a larger classification of thinking and you look at that as a bigger classification problem, you got to redo the digits and redo the alphabet for everything new that comes in the future. So one of the things I've been trying lately on a classification problem is to say you have two classes at an upper level, 1, at a lower level, 0, or something like that. Then the upper level is the target thing you're trying to recognize. I don't know, a cat's paw or something like that. The lower level is really anything else. So how do you sample over infinitely many different kinds of things to compare with the cat's paw? My idea was, let's just take the function produced by the neural network and lower it. Any idea about that? Because only the cat's paw will pull it up, but everything else lowers it. There'll be a general lowering that has nothing to do with samples.
Yeah, it's really tricky. So I don't want to dive too deep into that because I want to finish on time, and that sort of would take me off on a tangent. But this issue of estimating things that sort of don't belong to one class is a very difficult problem. And we did have a paper on that recently. I can't remember what the new title is because my student changed the title, but the original title, which you can still find by Google, is Does Your Network Know That a Cat is Not the Digit 6?
Yeah.
And it sort of argues that the problem you're talking about is very difficult, and the things that people use to detect if their neural network is getting a wonky input don't actually work. Or at least the ways that people do things like outlier detection, the way they evaluate them are often too optimistic. And so we've done an evaluation of tons of different ways to try and solve this problem. It's a very difficult problem, but check out the paper. It's pretty readable, and I think it's a nice, simple idea.
Thanks very much.
Okay, I'm going to jump into the next results just because I don't want to go over time. So that was our first result. That's just saying constant step size SGD is a good thing to do when you can interpolate the data. But now we said, can you go faster? And so there was this paper in 2013 where they used what's called Nesterov acceleration, and they showed that for fitting neural networks, you can sometimes improve the practical performance. This idea is very closely related to momentum, which people also know helps in practice. But all the existing analysis of stochastic algorithms with this type of momentum or Nesterov acceleration, they don't really get the full acceleration. And so this table is a little bit nasty, and I don't quite want to go through it today, but basically if you're in the deterministic setting, when you have acceleration, you go from number of training examples times condition number, in terms of number of gradients you need to get within epsilon solution, to number of training examples times square root of condition number. And so if you do SGD or variance reduction, you can't quite get the same benefit. So with variance bounded, you have this one term that just can't change. Acceleration can't change with the variance. When you do variance reduction, you can go from kappa to square root of n times kappa, but it only works in certain settings. When you have the SGC, you can actually go from kappa to square root of kappa. So this is actually the fastest method in that entire table. So under this condition, we have a new fastest stochastic gradient algorithm in sort of any setting. Yeah, so we showed full acceleration. Some special cases of that result were also shown around the same time by other people. Okay, this is the one I'm most excited about. It's called painless SGD. So the previous analyses of those under this condition relied on particular step sizes, and those step sizes relied on constants you don't know, like eigenvalues of the Hessian. And so if you use existing methods to set the step size, like meta-learning and heuristics and online learning and probabilistic line searches, none of those sort of keep the fast convergence. So we showed a simple way to set the step size as you go that keeps the fast convergence. So I'm not going to go over these results in detail, but basically we showed that with this particular line search, you get the optimal convergence rate in a bunch of different settings, from strongly convex through to non-convex. Here it is. It's basically combining two algorithms, one from the 1950s and one from the 1960s. So we have our stochastic gradient step, but then you check that the step size satisfies what's called the Amii condition, which is a standard textbook optimization line search. So we're just doing a line search, but you do a line search on the training example that you sample as opposed to on all the examples. Yeah, so backtrack if you don't improve cost on the batch relative to the norm of the batch's gradient. So that basically guarantees your step size is never too big. If you initialize your step sizes properly, they're never too small. And this basically says you do at least as well as the best constant step size. And in fact, you can do much better than the best constant step size. There's a little bit of cost to do this. You need an extra forward pass on every iteration, and an extra forward pass anytime you backtrack. In principle, we can get the median number of backtracking iterations down to 0 if you initialize your step sizes properly. So it's really just 1.5 times the cost of the usual stochastic gradient, but now you don't have to run it with different step sizes. You just run it with this line search to find the step size. And we did some experiments and it looks really promising. So we trained on a whole bunch of different problems and we compared to many, many different things. So this is just a sampling of comparing to different methods. So the algorithm from the last slide is this red one. And here we're plotting the test error over time. And you see that the red one actually works pretty well in many settings. So we found it worked better than standard things like atom and eta bound and tuning the SGD step size very carefully and things like that. So I think this is really promising. Okay, so now you might have some anxiety about what I just said. So to ease some of that, let me say you don't need to actually run it to the point of interpolating data. It just needs to be possible to interpolate the data for these theoretical results to hold. The results can also be modified to handle data that's close to being interpolated. So we didn't include this in our papers, but it's fairly straightforward. You just basically get an extra error depending on how close to interpolation you are. So you won't converge, but you'll get down to that error level. We also ran some experiments where we tried to control the degree of over-parameterization. So if it's really over-parameterized, then line search works great. If it's close, it still worked really well. Because if you're close, then the assumptions still characterize the behavior pretty well. If it wasn't even close to being over-parameterized, it actually catastrophically failed. And I think this is why people haven't proposed this before. So it's not a difficult idea. It's just taking ideas from the 1950s and 1960s, but you need to know which setting to apply it in. If you don't apply it in the right setting, it just doesn't work. So I'm guessing people tried this on small problems, found that it failed, and then just gave up. But it turns out it only works on big problems. Another group proposed a fairly similar method a few days after our paper came out. We've compared to like a ton of different ways people have proposed over the years to set the step size, and we're clobbering most of them. To add some anxiety or skepticism, so my students said that the neural networks experiments were all done with batch norm, which makes no sense in terms of our theory. But they've now redone the experiments and said the trends are basically the same. They had more difficulty getting it working for LSTMs, and I think they're still working on that. So for LSTMs, things didn't work as nicely. And we think that's because the examples have vastly different gradients. And then in some of the non-convex results, there's some extra assumptions that if you look carefully, maybe you shouldn't be super happy with. So for the non-convex setting, I'm not completely happy with the current theory. There's still some work to be done. Okay, let me do a final pause there, and maybe I can take one question, but then I'm gonna have to wrap up.
Just a quick question about the line you just crossed out there with the batch norm. Isn't that problematic if you have batch norm, because you'd likely no longer be interpolating? Or yeah, could you maybe explain that a little bit more?
Yeah, I haven't really thought about it, but I think I kind of agree with you, where if you have batch norm, it's not obvious how that interacts with the other assumptions at all. Like, it's not just the interpolation, but also the Lipschitz constant and things like that, how those sort of things change under batch norm. So I think that there's just more thinking to be done on that. I was just surprised that they were using that, given that it isn't justified by our theory at all, as far as I know. Okay, so let me just briefly mention the last one. So the reason you can't do stochastic Newton methods is because of the variance. They can only improve the dependence on the condition number, but not the variance. When you have SGC, you get rid of the variance asymptotically. So stochastic Newton methods now make sense. And so I have some great students pictured on the right there and collaborators, and they basically showed the things you would expect of a stochastic Newton method. So you basically get quadratic convergence as you approach the solution. They did analysis with like quasi-Newton versions and Hessian-free implementation so that you don't have a big runtime and so on. So it's kind of a neat paper, and that paper just came out last month, I guess. Okay, so let me wrap up. All right, so some take-home messages. If you have under-parameterized models, if you don't have a huge number of features or a huge neural network, variance reduction makes a lot of sense. But if you have over-parameterized models, you should not use variance reduction. So we gave a bunch of new algorithms and analyses for these over-parameterized settings. So we showed that plain SGD actually converges fast under these settings. We gave a faster SGD using acceleration. We gave an SGD that uses line search, so you don't have to set the step size, one less hyperparameter to worry about. And we gave a furious SGD with second order information that gets very fast convergence. So I think if you're training these big neural networks, I think it makes sense to try out the line search. So we have some code available, and we're trying to add it to standard packages. It'd be really helpful to know when it does and doesn't work to see what sort of things we might be missing, both in theory and practice. And then last December, people said that, well, maybe variance reduction actually still is relevant for deep learning. And in particular, there was a paper showing that for GANs, it still makes sense to use variance reduction. And so the story is maybe not quite as clean as I've indicated. The last thing I'll mention is this may get canceled because I may need to have a surgery in June, but I was planning to give an optimization for machine learning unofficial course and just invite all the people from the Western universities to come. So that'll probably be in the second half of June. It's definitely open to Amii people, so I'll probably send an email about that in the next few weeks. It'll be maybe starting 2 weeks after the NeurIPS deadline, and we'll cover a lot of the stuff I've talked about today in detail if you want to learn about these methods and other things like proximal gradient methods. I'll cover all the theory and algorithms behind that sort of stuff. So that might be of interest to many of you. Okay, I will stop there because I'm at the end of my time. Awkward Zoom clapping ensues.
Well, yeah, but if you can also raise clap by clicking on the reaction buttons. So maybe one or two very quick questions. Also, I'll remind people there are still 1 or 2 slots remaining. If you're interested in meeting with Mark, you can meet anytime you want, of course. You can send him email, try to connect with him. But today, he's sort of committed today to spend with us. If you're interested, contact Sabina and she can add you to a slot to meet with him. Questions? This course, how many? It's going to be like half day lectures for 5 days in a row or something like that. Is that the structure of it, or?
I have about 10 lectures, and so I don't know if it'll be 2 lectures a day.
Okay.
Or 1 lecture a day, but it'll be either 1 or 2 weeks, something like that. Probably 1 lecture a day, just because it's hard to take in a lot of this stuff. And I do go a little bit slower when I'm teaching, but I still go a bit fast.
Okay. And exercises as well?
I will suggest exercises, but it's not an official course, and I don't have the energy to make assignments. So I will just, during the lecture, I'll mention things that are easy to prove and things that are hard to prove, and I'll let that be self-directed.
Understood.
I guess I do have the assignments for my class that people can choose to do them if they want to.
Okay, good. Other questions? Okay. Okay, well, again, it's a little bit after 1 o'clock, so maybe we'll end it here. Sabine, anything else I should mention or talk about? There's a whole bunch of people saying, I don't know if you're seeing the Zoom group chat, a whole bunch of great talks and congratulations and thanks and claps and things. So, well done.
Great, cool.
Okay.
I hope
Okay.
people liked it. I know that this type of talk is not everybody's cup of tea, but I hope to at least give you an insight into what I've been thinking about for the last 11 years. And I think we've done some neat stuff.
Sounds like foundational topics that are already making a difference and will continue to make a difference. Last call for questions. If not, thank you very much. Okay, we'll end it here. Thank you very much.
Thank you so much for having me. Have a good weekend, everybody. Stay safe.
Again, people meeting with him, go to the Google Doc, Google Sheet to see how to connect with him.